All right, well, I guess it's time to get started. So welcome everybody to this session, session 15D, Origin of Life and on Earth and Beyond. Hopefully you had a chance before today to watch the great lectures from our great panelists, Natalie Batala, David Deemer, Tori Holer, and Hillary Hartnett. And we hope that you come prepared with many questions. Please write those out in the session chat, and we'll try to get through them all over the next hour. The structure of this hour is going to be as follows. We're going to give each of the speakers an opportunity to give a brief recap of their talk, and there'll be some questions around that. Then we'll do some broad questions, and then we'll turn it over to Q&A from the audience about halfway through. If you saw the presentations, then hopefully you saw them in the order that we intended, and that order was as follows with a bit of a logic to it. Natalie's presentation went first to give an overview of the state of the science of exoplanet hunting, one of the most exciting frontiers in astrobiology and hence in origin of life. Then Dave Deemer gave a look at a cutting edge and somewhat controversial idea about where and how life began. So we went from astronomy to prebiotic chemistry. And then Tori gave a perspective on what factors we need to consider when looking for life beyond Earth, particularly in our solar system. And then Hillary closed it out with a presentation on sort of an overview of what we really need to think about as geoscientists when we are looking for life on a planetary scale. So particularly when looking for life on extrasolar planets. So that was the overall what we were trying to achieve is this progression from the cutting edge of planetary discovery and origin of life through the kind of search strategies and things we need to consider when we look for life in the solar system and beyond. Sarah?
Okay, so just in case some people in the audience didn't get to see the amazing talks, which I really would recommend that you have a look at when you get a chance, I would like to start off by asking each of our panelists to give a lightning summary of their talk in 1 minute or less, and then we'll ask a couple of very focused questions on their particular talk. So could we start off with Natalie, please?
Sure. Hello, everybody. Welcome. So I gave a talk called The Plurality of Worlds. And as Ariel and Sarah mentioned, this is about planets orbiting other stars. We now know of over 4,000 planets orbiting other stars, and the large majority of them are planets that are relatively small, as in smaller than Neptune. So approaching terrestrial sizes, and some of them are even potentially habitable because they orbit in what's called the Goldilocks zone. These detection missions are giving us really just bulk properties like the radius or the total mass and the orbital period, maybe some knowledge of the host star itself. And from that information, we've discerned that there's a huge diversity out there, that the diversity of planets in the galaxy far outweighs the diversity of planets in our own solar system. And we suspect that this extends even to the planets that we would otherwise think are like Earth. And that has significant implications for life. So in the future, we're about to start this new epoch of exoplanet exploration, which is going to kick off with the James Webb Space Telescope, which will enable us to detect chemical tracers in the atmospheres of planets. And we want to map those chemical tracers to the bulk properties of planets in order to better understand the physical processes that drive this amazing diversity, which could either limit habitability as we think about it, or increase the real estate for habitability in ways that we hadn't thought of yet. So that's my summary of my talk.
Awesome. Thank you very much, Natalie. So from listening to your talk, it seems like the James Webb Space Telescope is going to be really important for your field over the next few years. Do you have a timeline of when that's going to be actually ready and up there and bringing back data?
So the last official word we had from NASA was that it was going to launch no sooner than March of 2021. Those plans have been foiled by the pandemic. So we still have people, it's considered a critical work. So there are still engineers working to prep the spacecraft for launch, but the whole process takes longer. The last I heard, though, we think it's still going to launch in 2021, but perhaps later, towards the later part of the year. An official date has not been given yet, but I'm relatively confident that it will be in 2021.
Brilliant, thank you. And the other thing I was wondering, well, one of many things I was wondering about from your talk, I learned that most sun-like stars have a planet around them. And I was wondering, does that apply to multiple planet systems? Do you think that something like our solar system with its 8 planets and some are gassy and some are rocky, do you think that's a common type of scenario?
Multi-planet systems are certainly very common. We see hundreds of them in the Kepler data, which is the primary mission that detected planets. In fact, we found new architectures that are somewhat unlike our own solar system. We know that planets in our own solar system orbit in a coplanar geometry, but it has some thickness. There are small variations, and it's kind of like a pancake, whereas other planetary systems, multiplanetary systems, are so highly coplanar that it's more like a thin crepe. We're trying to understand the difference between these different architectures. Unfortunately, with the Kepler data alone, we do not have the information required to say if the specific type of architecture of our own solar system is common or rare. Because if we looked at a system exactly like our solar system with Kepler, we might have seen one transiting planet or one eclipsing planet in that right geometry. So it's not until we launch missions like WFIRST in the future that we will have a more comprehensive picture of planetary systems from Mercury's all the way out to Jupiter, Saturn, Uranus, and Neptune's. Then we can really try to understand the broader picture of architecture.
Awesome. Thank you very much, Natalie. Okay, can we move on to Dave? Could you give a 1-minute summary?
Thank you, Sarah, and welcome to everybody listening in on this. Life, it's a given that life requires liquid water. On our planet, there's 2 kinds of liquid water. Most of it's in salty water of the ocean, and so it's been easy to assume that that had to be where life began. I'm a biophysicist, and I am not as much interested in the chemistry of the small molecules of life, where the field has focused for many years. I'm interested in how those chemicals can come together to form a system of molecules. These molecules that are in systems of life today are polymers. So we have to find a way for polymers to be assembled under prebiotic conditions. Life today is cellular. That means that probably cellular life goes all the way back to the beginning of life. So we have to find a way, a biophysical process by which polymers can be encapsulated. So that's what I've been working on. In my talk, I told you that an easier place to get these sorts of things to happen is in a freshwater environment. On Earth today, there is fresh water available as hydrothermal fields produced by precipitation falling on volcanic landmasses. We assume that there are volcanic landmasses on the early Earth emerging from the global ocean, and that is a place where, in fact, this kind of polymerization and encapsulation leading to what we call protocells could have begun. So that's what I'll be talking about.
Brilliant. Thank you, Dave. So can you summarize why you favor this freshwater hydrothermal environment rather than salty water?
I'm sorry, I didn't get the gist of your question.
Oh, sorry, could you summarize why you favor these freshwater hydrothermal fields?
Oh, sure.
Rather than a more saline environment?
Okay, think about hydrothermal vents, which is the place we've been thinking about in the ocean as a place that has the chemistry and the physics, actually, for the origin of life. That is a bulk phase water, meaning that if polymerization is going to happen, there has to be a way to extract water molecules from the reactants. These are the monomers of proteins and nucleic acids, which are amino acids and nucleotides. Somehow there has to be chemistry available to pull water out to make either ester bonds in the case of DNA and RNA, or proteins in the case of the long strands of peptides that we call proteins. in a bulk water environment, that is hard to do. The spontaneous reaction is always downhill to smaller and smaller molecules. You tend to break those ester or peptide bonds. What we have found is that on these wet-dry cycles that occur in volcanic land masses, precipitation makes things wet, it evaporates, it makes things dry. That drying process adds chemical energy that can cause polymerization to happen. So we've shown that in the laboratory, and we're going out into the field. We just got back from hot spring in New Zealand called Rotorua, and we've tested some of these ideas there, and we see these polymers being produced. Furthermore, if lipid is there, the polymers become encapsulated to form what we call protocells. When we tried that with salty seawater, it just doesn't work.
Wow, fascinating. Thank you. And do you think this kind of freshwater environment is common in the early Earth and on other planets as well?
The early Earth certainly had a global ocean, but there was no continents at the time that life began. When I talk to my geologist friends, they say there certainly were volcanic land masses. When we look at Mars, the surface of Mars, we see volcanoes going all the way back to over 3 billion years ago. Olympus Mons is the largest volcano in the solar system, almost 3 times the height of Mount Everest on the Earth from the surface of Mars to the top of that enormous volcanic area called, it's the size of France, in fact. This is truly big. There must have been the same kinds of hydrothermal activity, and these seas would have been evaporating water on early Mars. That water would have been falling on volcanic land masses and providing the fresh water on Mars. We don't think that that kind of thing could occur on icy moons. So I put a big question mark in my mind about the possibility of life emerging on icy moons, such as Enceladus and Europa, because we just don't have that kind of wet-dry cycle. And it's really hard to think of where the energy would come from on a icy moon.
Great. Thank you very much, Dave. So that brings us next to Tori. Could you summarize your talk for us, please?
Sure, yeah. Hi, everyone. So you heard Dave mention life's requirement for liquid water, and that understanding has actually driven about 2 decades of exploration in planetary science. We called it Follow the Water, a search for liquid water-bearing environments in our solar system. And that search has been so successful that now we have an abundance of riches. We have at least 6 ocean worlds. We have good evidence that the surface of Mars had abundant water in its past. And so I think we need to ask now, what comes next? What are the sensible next steps in exploring our solar system in the context of life, or the ability to host life? To me, there are 2 things that make sense to do. One is to look beyond water to life's other requirements in order to get a sense of detectability. And that's actually a word that both Hillary and I used in different contexts. By that, I mean, suppose that life was present. The mere presence of life doesn't guarantee the ability to detect it. You need to understand something about how robust it could be, how productive, and so forth. And I think by understanding the availability of resources, life's other requirements, so for the elemental raw materials and the energy and the other things that life requires, understanding the delivery of those things through time by the processes in the system really will help constrain how detectable a biosphere will be, how big a signal it presents to us. And that would give us an ability to try to narrow down among our prospective targets in a search for life. The other is to think in probabilistic terms. How likely is it that if the conditions are right, that life will actually emerge in an environment? Simply having a habitable place doesn't mean that life will be there to begin with. I don't think we really know the answer to that question, but framing it and putting it in the context of planetary sciences, for me, is the way that we link the exploration of the solar system to the theme of this session, which is an origin of life session after all. Thinking about where life can emerge, whether it emerges when conditions are right, is a way of, again, narrowing our sense of possibility for where life might be and how likely you are to find it. And so I think that's it.
Brilliant. Thank you very much, Tori. So this is, probably a difficult question, but how common do you expect life to be in our solar system outside the Earth?
Yeah, thanks for the softball question. Honest answer, I have no idea. And I don't feel bad about it because I don't think that anyone else really has an idea about it either.
Sure.
My intuitive sense of it, I think, comes from my background as a chemist. And to me, I think of the origin of life as being quite a challenging chemical problem. So my sense is that it's really not a very common thing for life to emerge, but that's a gut feeling. And others, I actually would be quite interested to hear what others think about it. I recently was in the context of a discussion that was mostly planetary sciences and then a few people who had more strictly chemical backgrounds. And I was surprised among the planetary sciences that their sense of probability was actually quite high. People thought that life would emerge quite commonly, and the people with a more chemical perspective thought that it was a bit more difficult thing. I would love to actually revisit that later in the discussion and actually hear from the audience as well.
Sure we will. And so what would be your favorite place to go to explore in the solar system to look for life?
Oh, wow. So I work actively with people in the Mars community and actively with the people in the Ocean Worlds community. And this seems like a question that was specifically designed to alienate me with one or the other of those groups. So let me do my best to give you an answer that's not really an answer. As many of you may know, there is an effort to return samples from Mars. And I think if that is able to go through, and so far so good, it would represent a remarkable opportunity to look for evidence of life. So let's take that as a given, and then I can say that I think the next exciting thing to do will be to look to the ocean worlds of our outer solar system. And actually, maybe it's worth mentioning in this context, the planetary sciences community and NASA are about to embark on a process exactly to try to understand the community's sense of what are the important priorities in the exploration of the solar system. It's called the decadal survey process. And it will set the priorities going forward for the next couple of decades. Where should we look? This time around, the decadal survey really strongly encompasses themes of habitability and life detection. And so it will be really interesting to see how the results of that process drive our sense of priority in the solar system exploration.
Brilliant, thank you. Exciting times ahead. Great, so shall we move on to Hilary, please, for your 1-minute summary?
Thanks, Sarah, and thanks, Ariel. It's been a real pleasure to be part of this session. So in my talk, I did the first thing you should never do in a talk, is I had 2 different messages, but they're kind of related. The first, and this is all coming from my perspective as a biogeochemist who tries to work really closely with astrophysicists and geophysicists and people from different disciplines. First is that there are important elements for biology that we know almost nothing about from a sort of astrophysics standpoint. And the key element is phosphorus, which Tori mentioned a little bit in his talk. Phosphorus is one of those elements that's extremely difficult to measure in stellar spectra. And so we have an actual dearth of data on the distribution of phosphorus in stars. And if we assume that stars get their element, or planets get their elements from their stars, then just the first principles question of how much phosphorus is there in stars is a question we can't answer. And so my colleague and I have been looking at the distribution of elements in nearby stars and trying to get a sense for what are the sort of general distributions of nitrogen and phosphorus and carbon. And the take-home message is we don't have enough phosphorus data. And so we really desperately need these new spectroscopic missions that will be able to measure things like phosphorus for us. So number 1, we need more phosphorus information. The second point is that a systems approach that looks a lot more like ecology than chemistry or geophysics or astrophysics might be really important for how we think about life on exoplanets or the potential for life on exoplanets. So I tend to think about this idea that the Earth has been inhabited for most of its 4.5 billion years, as far as we can tell. As soon as it wasn't hot and melty, it's pretty clear that there was life. So the Earth is an inhabited planet. It's a living planet. We have no abiotic Earth. And so the planets we discover that have life, it's going to be hard to know what they would have been like if they didn't have life. And so we have to think a little creatively about how we're going to balance processes that are abiotic, geochemical processes that might produce, say, a biosignature gas like oxygen, against processes like life that can produce oxygen. And we're going to need to know really firmly if that signal of oxygen that we might detect around in the atmosphere of an exoplanet, how sure are we that it's due to life and not just due to, say, photolysis of water in the atmosphere. And so we've developed this more quantitative index that looks at the production by biology versus the production by geochemistry. And you've got to use models to try to get your best estimate of both of those things to say, how sure are we that we think that oxygen could be driven by life as opposed to by the geology of the planet? And now that there's an index, and that index isn't just yes or no, you might want to consider prioritizing those planets where that index is high versus those planets where the index is, it's not so sure if it's life versus geology. And so that take-home message was sort of demonstrated for a water planet that has no continents, just an ocean. And it turns out a water planet, which could have liquid water and be perfectly warm and have photosynthetic life, might not have enough phosphorus in this case to support high rates of photosynthesis. And so the oxygen might not be distinguishable from an abiotic oxygen source. So it's a cautionary tale that planets that might look perfectly habitable to our sort of human-focused eyes, we need to think a little more carefully about what atmospheric signatures will look like in those planets.
Great, it's very, very thought-provoking, thank you. So if I could ask you a question about each of the two halves of your talk. So firstly about the abundance of the elements, and especially the bioessential elements in stars. I mean, is this, you know, you made the point very strongly that it's there's not very much data for phosphorus in stars, but is this something you can model? How would you expect the galaxy to evolve in terms of the abundance of these elements in stars? Can you use the age of a star to determine these
So that's
abundances?
a really good question, and it's a good thing I have an astrophysics colleague in my speed dial that I can call and ask this question before I came today.
Later then.
So there's kind of two parts to that question, right? We know that the total amounts of these kinds of elements will increase over time as the sort of process of stellar nucleosynthesis goes on, right? In the near term, we can try to think about what ratios of elements in stars might tell us, or either about how much we expect to see or about which elements are produced at the same time as the elements we care about. And so, you know, for instance, phosphorus and silica ratios should look about the same because they're co-produced. But phosphorus iron or phosphorus magnesium, other elements that are important for rock forming, for instance, might show different trends. And so there's a lot of work to be done both on understanding the production and distribution of those elements, in addition to the how are we going to measure those elements.
Great, thank you. And on your biodetectability index, so you're using the example of a watery planet, one where the water covered all of the rock, basically, so that they couldn't weather very fast. And I was wondering how common are these watery planets, or how common do you expect them to be?
Also a great question. And I feel like Natalie's probably more equipped to answer it than I am. It turns out the Earth is actually relatively dry, despite the fact that we look like we have a lot of water on a mass basis. We're pretty dry, right? Well under 1%, down in the sort of 10th percent by mass, our water. So we're not talking about planets that have 10, 15, 20% water, and those exist, right? We think some of the TRAPPIST planets could have that kind of water mass. But the water world that we talked about might have 1 to 2% water. And I'll just sort of answer it statistically, right? We have examples of planets that have less than 1% water, and we have examples of planets with 10, 15, maybe more % water. So I'm going to assume that there's probably a continuum.
Yeah.
I don't think it's all that unlikely. It's actually not that much more water than Earth has to cover the continents. We think you need about 5 Earth oceans of water.
Okay. Great, thank you very much, Yuri. So I'll pass over to Ariel to continue the discussion more broadly.
Great, thank you very much. Those were great summaries and great Q&As. We have some questions already coming out in the chat, and I'm sure other people want to raise their hands. So I'm just going to start it off though with asking one big question for all of you. Tori already kind of addressed this from his perspective. So it's a big question. In your opinion, your judgments, are we alone? what does each of you think about this question coming from your particular perspective and angle? So Tori, you kind of already addressed that, I think. If you want to elaborate on it for a second, you're welcome to. Otherwise, I'll just go around and ask the others.
Sure, I'll try to be brief. I don't think we're alone. If I did think we were alone, I don't think I'd be in the business that I'm in. But part of the reason for saying that is that even though I've said I think the origin of life is a challenging chemical problem, I think we're learning, especially from the exoplanet science, that there are likely vast numbers of environments where life might possibly emerge, where conditions might be fairly similar to our own, or conditions might be conducive to another form of life. And simply by virtue of those vast numbers, I think it's unlikely that we're alone.
Natalie, do you want to take a stab at that from an astronomer's perspective?
Well, until Tori made his comment about the chemists, I would have said, my perspective is that life got a toehold here on planet Earth almost immediately. As soon as the continents cooled down enough so that we had oceans, life got a toehold. And that leads me to believe that planets that have similar conditions will likely be living worlds, at least in a microbial sense. On the other hand, more complex life, multicellular life, and what we know as intelligent life didn't arise until eukaryotes were formed after something like 2 billion years. So that leads me to think that more complex life is going to be more rare. But now Dave Deemer is telling us that life might need these very specific conditions, and that gives me pause on, it's kind of like what I said before. Either the real estate for life is grander than we thought, is larger and broader than we thought, or we're going to end up prescribing to the rare earth hypothesis that all of these different coincidences had to converge. And the reality is we don't know which of it is. But my gut feeling is that nature is very creative and prolific, and in the absence of the exact right conditions, it's going to find alternative pathways. So I think life is going to be very common.
Dave, do you want to pick up on that, since Natalie took your work as a reference point?
Sure. I absolutely agree with the sense that we share, Natalie and I, probably the rest of the people here, that microbial life is probably easy to get to. It started up right away. We know from microfossils that there's fairly advanced microbial life around 3.5 billion years ago. The question is, are we alone? We mean that we have nervous systems capable of intelligence. And that is a huge jump, isn't it? That probably began in the Precambrian to Cambrian, where animal organisms began to be mobile. They had to have a nervous system at that point. And that, that to me, that is the real sort of stumbling block. How do you get to nervous systems aware of the local environment, able to respond, first just reflexively, but then finally able to begin to make little images in central nervous systems that allow us to manipulate images in our heads? The definition of intelligence, that we can problem solve in our heads and not just by a trial and error, by doing stuff out as an insect might do, for example. So I would think that, well, the other thing that comes to mind is Carl Sagan and his billions and billions. Billions of stars, billions of galaxies. How can there not be intelligent life out there with all of that? And that's where I sort of go along with what Tori said, that deep down, my guess is there's probably somebody out there, and we may be able to contact them with a huge barrier of tens to hundreds of light years, just getting signals back and forth, So it's wonderful to think about it. So much fun. And it would be just lovely if we get that one little signal coming in from outer space sometime in our lifetimes, and realize that we are not alone.
Thank you. Hillary, do you want to round out the panel on this question?
Sure. Let's see. To start with, I think that I am also firmly in team microbe. I think, you know, microbial life in various forms is probably easy. And I say that from the standpoint of a chemist, right? I think that the ways that the chemistry works are relatively limited, such that that kind of chemistry is probably going to happen somewhere. But I like Dave's perspective on the intelligent life, right? That is a much more, that's a heady question. And I'm going to put a slightly different spin on it that Ariel will appreciate. When I'm not an astrobiologist, I think a lot about the Anthropocene and what our sort of place as very modern humans is. And I think that finding out if there is other intelligent, communication-enabled, space-traveling life is a lot more likely to be a statistical unlikelihood, right? At this moment in time, our planet is oozing energy in all kinds of ways and all kinds of wavelengths because we're not very careful about it, right? And if we survive this Anthropocene, we're going to stop doing that the same way as we do it now, at which point we will be harder to see. Just like any other hypothetical, highly intelligent population at a stage that humans are at might also be hard to see. And so we're going to have to find that potentially rare opportunity that not only are we looking, but they're talking. And that is a needle in a haystack that I think we can dream about, but I don't feel so positive about.
Great. Thanks. So we have some questions coming in through the Q&A module. So people should feel free to type questions there, also in the chat. And you're also welcome to raise your hand, and our assistant, Maria, will can call on you and turn on your mic. So we have multiple ways to entertain questions. So let me start. I'll work on the questions that people have typed in and pass them along here. So there are a couple of questions of similar flavor around the question of you know, that we tend to focus our search for life on life as we know it, right? Based on phosphorus and nitrogen, based on water as a solvent. You know, exploration of the solar system tends to surprise us. Exploration beyond the solar system has also tended to surprise us. So with that in mind, in what ways might we be surprised? What sort of life as we don't know it might be out there? How do you think about that? And even here on Earth, one of the questions in the same similar vein asks, you know, how do we know that there is not or has not been alternative life, you know, non-DNA, non-RNA based life on Earth even? So I'll open it up. Whoever wants to take this question, wherever you want to take it. Life as we don't know it. How do you deal with it? How should we deal with it?
Maybe I should start off from the astrophysical perspective and just say that the most abundant elements that are created in the universe are also the most abundant elements in life. So from a physical and cosmological standpoint, it makes a lot of sense that life will be carbon-based, and even that life will use liquid water as the solvent required to facilitate important chemical reactions like metabolism. So yeah, I think I'll just leave it at that.
So carbon, water-based life, anybody want to take on those as good working assumptions?
I think maybe I can try to follow up a little bit what Natalie said, because there are a couple of takeaway messages that you might have from that, right? I had a paper recently where we compared the abundance of elements in the Earth's crust and oceans and atmosphere against what life uses. And as Natalie said, many of the ones that are most common in life are also the ones that are most commonly available. So do you take from that we're built of that stuff simply because that's what was there, and that if you had other abundant stuff elsewhere, that life could just as easily make itself from that? Or do you take away that if those things are common in the universe and in planets, that there's no need to think about other stuff because you're always going to have what you need? I think we can look at our own solar system at a place like Titan to wonder why we may ask this question, right? Titan is an environment where you have a liquid environment into which a great deal of energy flows. It's the only other place in the solar system where you have sunlight flowing into a liquid environment, in that case, a liquid hydrocarbon environment. It's interesting to ask that question. So I think that Carl Sagan described himself as a carbon chauvinist, but not a water chauvinist, right? Implying that carbon is necessary as a backbone for life, but that life could find itself working in any old solvent. as I personally have thought about this a little bit, there are a lot of quite unique properties of water or solvents very like water that make it a very useful medium for biochemistry. And I'd be interested to hear Dave and others' take on whether we should all be water chauvinists as well.
Yeah, so what about a ethane or a methane ocean as a place for something resembling life to occur? You know, life is chemical. It's chemical bonds being made and broken. And life is polymeric. And it's really not easy to imagine a way to make and break chemical bonds in a methane-ethane ocean. We don't even know of those kinds of chemistry going on, despite the fact that we've been doing chemistry for 100 or more years here on Earth. Those sorts of reactions just are not, they're hard. We can't make them happen. So if we cannot find them in chemistry that we know about, it's really a huge stretch of the imagination to imagine that somehow something resembling polymerization and encapsulation and energy transfer, all the stuff that happens so easily here in life on Earth. How could that happen at minus whatever degrees that it takes to get down to liquid methane and liquid ethane? So to me, that kind of excludes Titan, which of course Carl Sagan loved. He just thought it was really neat. And I played around with a little bit with tholins and things like that, with some of the people that Carl has inspired by that. But boy, when you really get down to it, it's hard to make living systems work in an environment other than water, because water is easily chemically extracted from between monomers to make a link, and it's easily put back into that same bond to break it down again. And most of us don't know it, but we're doing that all the time. Life is in a continuous process of synthesis and breakdown. And you've got to have that in a methane ocean if you're going to have something resembling life there.
And of course, the temperatures at which these hydrocarbons are in liquid form are very low. So just the rate of chemical reactions that produces complexity are going to proceed much more slowly.
Yep.
So Hillary, do you want to address this question and maybe from the angle of nutrients and elements like phosphorus?
Sure. So if I recall, the question is about life as we don't know it, right?
Right.
And I'm going to start with, we focus on life as we know it because at least then we know what to look for, right? We do want to look at atmospheres and look for biosignatures that we know that they're a biosignature, at least for Earth. To look for something as a biosignature for a metabolism or a form of life that we don't know what it is, it's a much harder question. Phosphorus is an interesting one, right? Biology on Earth chose phosphorus, and there are actually quite a few reasons that make sense for why biology chose phosphorus. And there's not very many other elements in the periodic table that will do what phosphorus can do, both in terms of the strength of the bonds that it makes, the lack of redox chemistry that it has, the shapes and forms of the solid oxides that it makes. And so there's a few that you could go down a list, right? You could look at sulfate, you could look at arsenate, you could look at a couple other examples, but very few of them seem to have all of the sort of key attributes that life capitalizes on for phosphate, and in particular the orthophosphate anion. So strangely, phosphorus is somewhat unique in the periodic table for the things that it can do. I'm not saying that some other form of life couldn't choose some other element, but biology settled on phosphorus, and phosphorus is actually one of a very few things that can do what it does. I'm going to put another idea out there, and that's that there are people, colleagues of mine at ASU, Sarah Walker, who thinks entirely differently about how we could look for life, and it doesn't have anything to do with our particular types of metabolism. She's thinking about it as a physicist who is imagining the idea that life creates information density that's different from the information density in, say, rocks. And that's a super intriguing idea about how would you look for life in a way that's agnostic to the type of organism or the kind of metabolism. I don't know that we have any idea how to do it yet, but I think we're going to have to start to think in those kinds of ways about what are characteristics of life that are not necessarily the chemistry sometimes. So I think we do have to think extremely broadly as we start looking to other planets about what life's going to be like.
So
Could I ask a follow-up question,
ahead.
Hillary?
Please.
Hillary, I was surprised. I just didn't realize this problem that you brought up about it's hard to detect phosphorus as a origin. So we know that all the way up to iron, we can make elements by stellar nucleosynthesis. And some of the easy ones like carbon, oxygen, and nitrogen are surprisingly easy to make, and we've known that for over 50 years now. Is there a known nucleosynthetic pathway to phosphorus in stellar nucleosynthesis?
To the best of my knowledge, the answer is yes. It's easy, you can make it. The reason we don't know much about it is actually a problem of the spectral lines for phosphorus. They are relatively weak. They're you can measure it in the infrared, but it's at about 1 micron wavelength, which is a sort of problematic window. It's hard to measure from the surface of the Earth because there's a water interference. And you need relatively high resolution to pick it out. There's some hope that we can measure it in the UV, and so some of the new proposed telescopes like HabEx and LUVOIR might be able to do it. You could build a high resolution spectrograph to measure it specifically, but you'd want to put it on a satellite. So it's not impossible. There's some data. There's about 90 stars in the Hypatia catalog with phosphorus data. But that 90 is sort of piddling in the face of the 6,000 that we have iron data for, or silicon data for. And when you start to look at ratios, it gets even worse, because then you have to say, was I lucky enough to have phosphorus and nitrogen and carbon data in the same star? And so I think it's partly just a perspective on which elements we want to know about, that has limited the way we've collected the data. So I'm actually encouraging my astrophysics colleagues to find me phosphorus spectra.
I mean, phosphorus is indeed produced in the nucleosynthetic pathways, Dave, that are happening in the cores of the most massive stars. Through the study of galactic kind of archaeology, we can probe these chemicals, and we've learned a lot. We can make a periodic table that shows every element and shows where in the universe all of those elements were formed. And phosphorus in particular was formed, we think, in the cores of the heaviest stars, which is a certain type of supernova that happened early on in the formation of the galaxy.
Okay.
So it should be readily available in in many stars, in most stars. But
So,
like Marie said, the devil's in the details, so the small variations matter a lot.
So we touched on what we should be looking for, and so there are some questions that really go right there. And so I'd like to ask you, what makes for a good biosignature? What should we be looking for? And is there a smoking gun? Right? How will we know it when we see it?
I mean, my perspective is specific to exoplanets. So when we're talking about finding life on exoplanets, we're thinking about remote detections. We're not going to go there to see that there's life. And when you're talking about a remote detection, it means you're also not looking for life that are hidden away in niches, like in a subsurface ocean or in a subsurface cave someplace. We need to find biosignatures that are evidence of a global biosphere where life has taken a global toehold of that entire planet. Otherwise, we won't see it. So those kinds of biosignatures have been thought about a lot. For our own Earth, the global biosignature is oxygen, as produced by photosynthesis globally, this metabolic byproduct of photosynthesis. And there are false positive signatures. There are ways that we can be fooled. Hillary mentioned the photolysis of water that allows hydrogen to escape, leaving behind an oxygen abundance that is not due to photosynthesis. So we have to be careful. For me, what I'm thinking about in the future is really to understand what life is, we must understand what life is not. And that means that we need to look to have this statistical picture of what exoplanet atmospheres are like, in order to pick out what I think is going to be kind of something that sticks out like a sore thumb. Life should look inherently different. It should also be an indication of disequilibrium chemistry that is happening, sources that are continuously replenishing, species that get destroyed by normal atmospheric photochemistry. So those are the kinds of things that we're going to be looking for. But I think first we have to get this really broad understanding of what exoplanet atmospheres are like statistically to understand the broader context.
Well, Natalie raises a really good point, right? This idea of what life is not is another way to say that is we need to be really good geologists. We need to know how planets work. We need to know how geophysical processes that move heat and elements and everything about what planets do operates, because for the moment, we're going to have to say, okay, we think we know how planets work and how much they could generate of a particular species that we might want to consider as a biosignature. And we're going to have a really good model that says this is what's possible in the absence of life. And we're going to have to compare that to what we see in the atmosphere of a planet, right? And so we have to actually, coupled to being able to see them and all the technology for astrophysics to actually be able to do those spectroscopy and a knowledge of what the biology is, we've got to have an absolutely solid understanding of what rocky planets do, right? And the systems in which life evolves. And so there's got to be this neat integration of sort of the way planets evolve, just the way life evolves.
How these elements are shifting from one reservoir to another, you know, and that goes all the way back to galactic chemistry, to the protoplanetary disks, when the planets are forming and how those elements get locked up into rocks that are later outgassed, you know, from the planetary interior and end up in secondary atmospheres that we then observe. That whole process. I mean, Hillary described herself as a biogeochemical modeler. that encompasses a lot, but it's really how these volatiles, how these light elements that, like those that are critical for life, end up in an atmosphere.
Yeah, I agree very much with that perspective. Sorry, did you want to go ahead, Dave?
Oh, I can say something about biosignatures in a Mars return sample. And let's just take a minute or so to get this point across. It's very likely we're going to see organic compounds. You know, we can analyze things down to parts per billion range now. So we're going to see organic material. So how do we know whether that is passed through a metabolic process or not? Well, that material they're going to bring back is probably millions of years old, perhaps even a billion years old, because we're going to be getting it from down, digging down, not from the surface. There's not going to be much there. We'll have to bring it up from someplace where we've gotten deeper down. So we bring up this stuff, we detect, we bring it back to Earth, and sure enough, there's organic compounds. And what we're going to discover is that probably it's going to be oily. Hydrocarbons survive millions of years here on Earth. You know, we are burning off fossil fuel. That was all produced by microorganisms. There are no amino acids in fossil fuels. Everything else is gone except for hydrocarbons, which have survived. So that's what we're going to see. So the biosignature that we can see in hydrocarbons on the Earth are specialized molecules that are only produced by metabolism. One of these is that we add carbon 2 atoms at a time, 2 carbons at a time, when we make fat, you know, when we make fatty acids, and that's what all life does. In fact, it adds 2 carbons at a time. So there is a signal built into fossil fuels that says, yes, that is from something that went through life. They are not just random hydrocarbons such as we would see in a carbonaceous meteorite. So I think that's an important point to remember, that there are special kinds of molecules that contain biosignatures, and that's what I would look for if I had a Mars sample return in my lab.
I was just going to sort of follow up on the earlier point. I think the problem of avoiding false positives is, as much as anything, a problem of understanding the full range of what's possible in the absence of life. And in that sense, it's transposable from exoplanets to planets in our own solar system. It's just that the kinds of evidence we can hope to collect are different. In the one case, it's photons that may tell us something about an atmosphere or the colors on the surface. In the case of our solar system, it may be physical material that we can actually reach out and touch and analyze. But in either case, there's really a problem of understanding the complexity of the environment and the history of the environment that can have produced abiotic mimics to the things we see as biosignatures. Life is capable of all kinds of amazing stuff, chemistry and so forth. So is abiotic process. It's remarkable if you look at the sorts of chemistry, for example, that seems to be possible in meteorites or comets or things like that. You can get quite a diversity. And so I think there's a real challenge in understanding the range of environmental diversity that's possible in a relative absence of observational constraint, right? We know a little about these places, but not a lot about these places. And yet we hope to understand what's possible as an abiotic background based on that sample. And I think it really makes the point that anytime we're going to bring something forward that we think of as evidence for life, we ought to have done the best job we can of constraining the environmental context in the place that evidence comes from, because it really is critical to the story.
I'd just like to follow up a little bit with the question on this planetary scale. I'm thinking especially about exoplanets. Natalie, you mentioned the notion of looking for deviations from equilibrium chemistry, right? And this being a geochemistry conference, that's like music to people's ears, is thinking in those terms. But when we think about microbial life, right, for certainly the first phase of Earth history, the first phase of life on Earth, and this isn't just a question for Natalie, it's for Hillary and anybody. The role of life was not so much to create disequilibrium as it was to catalyze the approach to equilibrium. This is a point that my colleague at ASU, Everett Schock, likes to point out quite a lot. That chemoautotrophs, they're essentially accelerating the heat death of the universe, or at least at the planetary level. And so, how do you detect those biospheres? And does that limit us, right? Are we really stuck in the exoplanetary sense, looking for those biospheres that are already pretty advanced, even though they're still microbial, and that they're capturing photons, they're driving dramatic disequilibrium energy through photosynthesis? So that's a question for anybody, maybe for Hillary first, but anybody can pick it up. I know Hillary's thought about it because it's the kind of thing we talk about at ASU every once in a while.
Well, it's a really good question, right? If life is actually capitalizing on the planetary disequilibrium, right, which fully the majority of life on Earth may still be doing in some way, shape, or form. Not everything is photosynthetic, right? Last I checked, I still eat organic matter, and so do lots of other kinds of organisms. So the way I would put it to you is that it's the word that's key is that word catalysis, right? Life makes things happen faster. It can't cheat thermodynamics, right? It can't do reactions that are not possible, but it speeds things up. And that's an interesting concept, right? Now we start to say, okay, there's a kinetic aspect to life that maybe is a biosignature in its own right, but we don't look for things that way, right? We take snapshots, we get individual, data points, and we don't always get to go back and look again. And so there are things that life does that might have temporal signals associated with them that we should also be considering, right? Imagine the Keeling curve, to go back to my ever so slightly Anthropocene bias, right? We have this CO2 increasing in the atmosphere at an exponential rate, close to exponential. That increase with the big curve is a human signal, but that curve has a beautiful seasonal cycle associated with it that is the tilted planet has a winter and a summer, and so biology has this seasonal variation due to a strictly sort of planetary orbital characteristic. And so we might want to be thinking about looking for other aspects of life that aren't just disequilibrium because we've learned to harvest energy from our sun. Chemically, I don't know exactly how to look for a chemosynthetic system.
Anybody else want to pick up on that? Equilibrium versus disequilibrium and how it plays into the search for life and thinking about origins?
Sure,
I want to hear what Tori's going to say. I just one tiny thing that you made me think of is this idea of time scale, right? I mean, most of what's going on is happening on a geological time scale, and life is certainly fast compared to that. But we were talking earlier about the possibility of hydrocarbons being a solvent for life, and the fact that chemical reactions proceed much more slowly. And you know, I'm wondering about the evolution in a slower environment like that. And I love to think about the planets orbiting M dwarfs. The M dwarfs are the very low mass stars. And the thing about M dwarfs is that they are fusing hydrogen into helium very slowly, and they can live up to trillions of years. So our whole concept of time, you know, we have to be very careful about our own perspective related to time. And the heyday of life could be in the future, and it could be through these slower processes that we don't typically think about. Sorry, Tori.
No problem. I'm just going to pick up the same thread a little bit, because the problem really is when you have chemosynthetic life, so life that is extracting the chemical energy of the environment around it, it's doing something that's going to happen anyway. And it really is just a question of differing timescales. Life usually does it, you know, sort of a million or so times faster than is possible by the abiotic background. But there are a couple of subtleties. I think that oftentimes on the way to catalyzing that equilibrium, life can be a little bit leaky. And so you can have, for example, intermediate compounds that come out, especially if the life is moving fast in the course of catalyzing that equilibrium. Those can be things that you know, while they stand a little bit shy of being as information rich as our biological molecules, for example, they can nonetheless be things that are challenging to find as a result of abiotic process. So I think there's one hope there. The more efficient and the more effective life is at catalyzing that equilibrium, the more our chances there diminish. The other subtle thing, I think, is that while life catalyzes equilibrium, it does not catalyze reactions to thermodynamic equilibrium typically. The point is to extract and store energy. And in the course of doing that, it means that life pulls equilibrium down to the point at which that energy is enough to then allow us to store our own energy as ATP or something like that. So if you go out into environments that are primarily chemosynthetic, and you look at the chemistry, you look at the products and reactants of the chemistry that's being catalyzed for metabolism, you don't find those things being catalyzed down to equilibrium. You find them stopping shy. And the stopping shy point is the point at which energy is conserved. So life is faster, but doesn't take things quite as far on the road to equilibrium. And those are two subtleties that, you know, I don't know whether they represent viable toeholds for finding chemosynthetic biospheres, especially, you know, from sort of interstellar distances. But it's one way that I think life is distinguished from abiotic process.
Great, thanks. So looking at the clock, we need to start winding down. So first of all, I want to thank everybody who asked questions that we didn't get to. I'm sorry, and thank, of course, everybody who asked questions we did get to. I'm going to ask one quick exit question for all of you. We'll just take them in order from Natalie through to Hillary. Place your bets. Where will we find life first, assuming we find it, in the solar system or outside it, and why? Just quickly.
You know, I have to say exoplanets, right?
You don't have to.
Yeah, I think that exoplanets, because I think that we have the ability to observe dozens of potential environments for life. So I think we will get a statistical perspective more quickly.
Great, thanks. Dave?
Yeah, I would have to say Mars. Life may still be hanging on there. I would just give it a good 50-50 chance that we are going to find something, either past or present life on Mars.
Tori.
Another question to get me into trouble with my friends in the planetary community. I think I will go with the exoplanet side of things, because I think as time goes on and our technological capabilities advance, we'll have the ability to observe more and more worlds. And the number of worlds in our solar system remains fixed. And so I think as we expand that real estate, that gives us more and more possibilities for detecting life.
Well said, Terry.
Right. Hillary, last word.
Okay. I'm gonna fall back on my oceanographic roots and my great love of hydrothermal systems. And I'm gonna say, I think there's some reasonable potential for these ocean worlds in our own solar system, whether it's Enceladus or Europa. I think there's a lot of information we're going to get when we get to measure chemistry in those plumes, and we're going to learn something probably along the lines of what Tori's talking about, and that there are things that exist at this metastable concentration that can't be explained very easily.
All right, split panel. That's awesome. Sarah, back to you.
Great. Well, I'd just like to finish off by saying thank you so much for our amazing panelists. It's been the hour has whizzed by for me, at least, and I've learned loads of stuff, and I've really enjoyed hearing all your thoughts. So thank you so much. Ariel and I would also really like to thank Adina Payton, who really devised this session, and it's all her brainchild. So thank you, Adina. Thank you, audience. We didn't get through so many of your questions. I'm really sorry, but the good news is we're going to do all of this again in a few hours' time, so we'll try and get to some of the questions then. So hope to see many of you back here at 2:30 my time, 2:30 a.m. in London, but hopefully at a more reasonable time for you people in the US. Okay, so thank you very much, and bye.
Thank you all.